Let us proceed. In key question number 5, I ask you to infer the formulas for certain compounds by using the examples of the binary ionic compounds found in this table in teaching model number 1. The idea is we want to look for patterns. Consider the first compound, sodium chloride. Why does it have that particular formula? Well, let's look at the charges we would expect for the sodium ion and for the chloride ion. These charges are entirely predictable based on the position of the element in the periodic table. So sodium is an alkali metal. It has a cation with a +1 charge. The chloride is a halogen. It has an anion with a -1 charge. Notice that when we put these ions together, we would expect a formula of NaCl because the positive cation has to balance the charge of the negative anion. In other words, the total charge of the cation equals the total charge of the anion. In a similar way, consider magnesium chloride. Magnesium, we know, is an alkaline earth metal, and all alkaline earth metals produce a +2 charged cation. The chlorine is a halogen, which produces a -1 charge. There are 2 of them. Therefore, you can see that once the charges are balanced, the charge of the cation has to equal the total charge of the anion. Further, consider the example of potassium nitride. The potassium is an alkali metal. Therefore, we know it has a +1 charge for the cation. The nitrogen has a -3 charged anion. Therefore, 3 potassium ions are required to balance the -3 charge of the nitrogen because each ion contributes a +1 charge. In all cases, the total charge associated with the cation must equal the total charge associated with the anion. The key question number 6 questions what must be balanced in an ionic compound. Well, simply put, the total charge of the cation must equal the total charge of the anion. These have been examples of binary ionic compounds. Binary means, of course, that there are 2 elements in the compound. Ionic means, in most cases, that there's a metal cation and a non-metal anion. You might notice in that writing the name of the compound, we write the name of the metal first, then the name of the non-metal. However, the name of the nonmetal is changed a bit in the sense that the suffix or the ending is always "ide," I-D-E. This will always be true for binary compounds in general. The suffix is always I-D-E. To summarize, binary compounds have 2 elements. Binary ionic compounds consist of a metal cation and a nonmetal anion, and binary compounds always have the suffix "ide." We can now take a look at these other examples of lithium nitride, calcium iodide, and aluminum oxide. Please apply the principles we've just discussed in writing the formula for the following binary ionic compounds. Here are the answers for these 3 examples. I will discuss briefly the aluminum oxide example. The predicted charge for the aluminum cation is +3. And the oxide anion is -2. In order for the charges to balance, in a sense, we need to find a common denominator charge. And the common denominator charge here would be +6 and -6. In other words, we would need 2 aluminum cations and 3 oxygen anions to give the total charges of +6 and -6, so that in the end the formula will be Al2O3. This is entirely predictable based on the position of the elements in the periodic table. Let us move to explore the transition elements in ionic compounds. As we've discussed previously, the charges of the transition metal cations are less predictable. In many cases, Roman numerals are needed in the naming of ionic compounds that contain transition metal cations. Let's dissect what's going on. Let's break apart the formula of these ionic compounds so that we can see the charges on the sulfur and the charges on each of the metals. In each case, because the sulfur is found in the 6th column, its anion has a -2 charge. This allows us to predict the charges of the metals. In the first case, because we have 2 copper cations, each copper cation has to be +1. In the second case, because we have one copper cation, the copper cation has to have a +2 charge. And we can also predict that the silver cation charge must be +1. Now you can see that we've written the name copper Roman numeral 1 sulfide for the first case. I hope you can appreciate that the Roman numeral number 1 is referring to what the charge is of the cation, not how many copper ions are in the compound. We need to add the Roman numeral because the copper has variable charges. Copper 2, Roman numeral 2, is referring to the charge of the copper cation in the compound. So copper Roman numeral 1 refers to +1 charge. Copper Roman numeral 2 refers to a +2 charge. These are necessary. You cannot leave them out of naming a compound. If you just say copper sulfide, we don't know which particular compound you are referring to. But notice, we did not include a Roman numeral for silver sulfide. This is because silver is one of those transition elements that doesn't have a variable charge. Let's go back to the model periodic table that we have on the first page. You can see that there are certain elements, such as zinc, cadmium, and silver, that are highlighted in green. These transition elements are unique in that they do not have variable charges. In this context, I would argue that for the most part, what we've been looking at so far in this video is not something that involves memorization. If you know where the elements are in the periodic table, you can predict their charges for the most part for the main group elements. For the transition elements, you can recognize that their cations can have variable charges. But if you use a Roman numeral, you can figure out what the charge is. Or based on how many of the metal cations present in the compound and combined with a nonmetal, you can figure again what the charge is. I do need you, however, to remember that zinc, cadmium, and silver cations do not have variable charges. Therefore, they do not need, nor should you put, Roman numerals to indicate what the charge is in an ionic compound. Their charges are fixed. Silver cation is always +1, zinc cation is always +2, cadmium cation is always +2. Let's practice with this a bit, in that I'd like you to consider the two compounds Fe2O3 and mercury 1 bromide. For the FeO23, I'd like you to write its name, and for the mercury 1 bromide, I'd like you to write the formula. In the first case, for the Fe2O3, I hope you recognize the iron as being a transition element. It's not one of the ones such as zinc and cadmium that have a fixed charge. Therefore, you need to be able to write the Roman numeral to indicate which particular iron cation we have in the compound. Given the formula, the only way the charges can be balanced is when the iron cation has a +3 charge. There are two of them, so altogether a +6 positive charge, and there are 3 oxygen anions, altogether a -6 charge. Therefore, we call this compound iron 3 oxide. For the mercury 1 bromide, this of course is indicating that the mercury cation has a +1 charge. The formula for this compound is the following. Now this might come as a bit of a surprise to you because you might have predicted simply HgBr. Let me go back to the previous slide for a minute. Please note that mercury either comes as Hg2, 2+, or Hg2+. So a mercury cation overall has a +2 charge. However, it will be the Hg2, 2+, that is the mercury with a +1 charge. Let me explain that a little bit more. If you have Hg2, 2+, this means that each instance of the mercury has a +1 charge. Together, they sum to an overall +2 charge. This is an example of a diatomic metal. But if you simply have mercury +2, then each mercury cation has a +2 charge. So if we ask for mercury 2 bromide, the formula for that would be simply Hgbr2. This is a more tricky example, but fortunately it's the only one that's like this. Please look at exercise number 1 and complete the following table. You may wish to stop the video so that you can do this on your own time before you see the answers. Please compare your answers to the ones given here. Be sure to follow up with me if you're not clear about the answers.